Today we're going to talk about the fundamental theorem of calculus. Um, so more than halfway through the year and we're just now getting to the fundamental theorem, but here we go. The definite integrals, it says that differentiation and definite integrals, which we know is integration, are inverse operations. So all we're saying here is that if I were to take the derivative, so derivative of like y equals x squared, then y prime would equal 2x. And if I integrate 2x, then we know that I get 2x squared over 2 plus c, or just x squared plus c. So they undo each other. We get that function that we began with. And so these operations undo each other. All right, so in terms of what we're looking at on a graph, we know that to approximate the slope of the tangent line, we did the change in y over change in x, and we took the limit. So, but it was the limit of this secant line of y divided by x, change in y divided by change in x. But to approximate the area under the curve, what we're doing is multiplying the change in y times the change in x. These are like the rectangles that we've been finding. So to find the slope of the tangent line, we're dividing. To find the area, we multiply. So again, it helps us to kind of understand why these two different things undo one another. So we're going to talk about using velocity to investigate this fundamental theorem and how, once again, we can see how they undo each other. So if we're given this position equation, 2x squared plus 1, and they ask us to find the displacement would just be s of 2 minus s of 0. So if I put 2 in here, 2 squared is 4 times 2 is 8 plus 1 is 9, minus, if I put 0 in here, I get 1. So the displacement is 8. So let's look at that another way. If I take the derivative of this function, which would give me the velocity, derivative of position is velocity, I would get 4x. So now they're asking me to use this equation to find the area under the curve from 0 to 2. So I'm going to graph y equals 4x. So up 4 and over 1. Look at this line. And it wants me to find the area from 0 to 2. So it's this triangle in here. Okay. So the area of that triangle is 1/2 the base, which is 2 units, times the height, which is 8 units. So 1/2 of 16 is 8. So displacement in this case and this area seem to be the same. So let's tie that into our integrals. If we integrate from 0 to 2 this function 4x, then I'm getting s of 2 minus s of 0, because I know that this area, this represents the area under the curve, and this is my geometric area under the curve, and I know that this was 8 and it equaled this, s of 2 minus s of 0. So what we're saying here is that anytime I integrate a function, I'm going to get whatever the original function was, because this is velocity. We went back to position, right? So this function, going back to the original, we use a capital F to talk about the original function. So it would be f of b minus f of a. B minus a, top minus bottom. And this is the way that we can evaluate a definite integral other than just finding the area using geometry. So this is our fundamental theorem of calculus. It says that the integral of a function from a to b is f of b minus f of a, always top minus bottom. Now this function that we're talking about inside here has to be continuous on the interval from a to b, including a and b, and we have to be able to take the derivative from a to b. So, and the derivative of this function has to be this one. So again, we went back to the original function. So, sorry, I was just talking about this part right here. So we're going to do a few examples here. Now this is the same thing that I was just saying. Now we have a way to find the antiderivative of f, or the integral of f, which would give us the area under the curve. So this is what we just were talking about. And we also have these properties that they are talking about here, which, if you look at them, make a lot of sense. This one is saying that if I were to go backwards to the original function, it would be f of a minus f of a, because it goes from a to a. Well, if we subtract one number from itself, we get 0. This one is saying that if I were to integrate, and notice where the placement is, if I integrate from b to a, that's going to be equivalent to the negative integral from a to b. So if you switch these out, because they're supposed to go from low to high, if we have to switch them out to go low to high, we also have to make it negative. And then here, it's kind of like the properties that you learned back in algebra. What it's saying here is that if C happens to fall somewhere in between A and B, then we could split up these integrals and go from A to C and then add in C to B, and it's the same as the overall interval from A to B. So if C falls in between, then we can split these up. And sometimes we need to split them up because the function changes, like an absolute value function, for example. So we'll look at how all of these apply to our examples. So for this first one, it wants us to integrate from 1 to 2 the function x squared minus 3. So we're first going to use our rules of integration, or our add 1 rule. So we're going to get x cubed over 3 minus 3x. And we're going to evaluate that from 1 to 2. So if I put in 2, put the top number in first, 2 cubed will be 8/3. Minus, put in 2, I get 6. That's like my s of 2. And then I'm going to subtract from that, plug in the 1. So 1/3 minus 3. Okay. So we have 8/3 minus 6 minus 1/3 plus 3. Well, 8/3 minus 1/3 would be 7/3. Negative 6 plus 3 would be minus 3. And so that gives me 7/3 minus 9/3, which would give me negative 2/3. So this is saying that the area under the curve is negative. The overall area is negative. Well, if we were to think a little bit about what this graph looks like, This is a squared function graph shifted down 3. So it looks something like this. We were going from 1 to 2. 2 would actually be out here somewhere, I believe. So what we're saying is that the area between the curve and the top and the curve and the x-axis down here, there's more negative area than there is positive area. All right, for our next example, we have the integral from 1 to 4 of 3 times the square root of x. So remember, at this constant, we can move it out to the front. So we'd have 3 times the integral from 1 to 4 of, and we want to rewrite this so that we can use our power rule. So we're going to write it as x to the 1/2. And then we just add 1. So this will be x to the 3/2 over 3/2, or times 2/3. Now don't forget that this is all still times 3. And we're going to evaluate this from 1 to 4. So we plug in the top number first. So when I plug in the 4, the square root of 4 is 2. 2 to the 3rd power is 8. 8 times 2 is 16 over 3. So I get 16/3 minus, and then I plug in the 1. The square root of 1 is 1. 1 cubed is 1. 1 times 2 is 2. So I get 2 over 3. So now I've got 3 times 14/3. The 3's will divide out, and I just get 14. So this represents a positive area. And if we were going to look at this one is the square root function graph. It's got a stretch on it of 3. It's pretty tall. We're going from 1 to 4. So all of that area would be positive under that curve. Okay, so let's look at the absolute value one. This one is the one where that rule that says that we can break it apart is going to come in, because remember that this function changes the slope at x equals 1/2. So it looks kind of like this. At 1/2, it's going up on this side and up on that side, the absolute value. So we're going from 0 to 2, which means we're passing through the place where it changes. It's actually 2 different lines, one with a negative slope, one with a positive slope. So remember, we always break these absolute values up. So this one is going to be negative of 2x minus 1 for all of the x's on the left. And it's going to be positive 2x minus 1 for all the x's to the right of 1/2. So whenever I write this integral, I'm going to have to separate it out at 1/2. Because from 0 to 1/2, I've got to use this one. So from 0 to 1/2, I want to integrate negative of 2x minus 1. And then I'm going to have to add to that from 1/2 to 2 of the positive 2x minus 1. Okay? So an absolute value is a good example of one that we would need to split up. So let's go ahead and integrate that. So for this one, the negative is just like a -1. So we're just going to kind of leave it out here. When we integrate this, we get 2 times x squared over 2, or just x squared, minus x. And that one we're supposed to evaluate from 0 to 1/2. And then for this one, same thing's going to happen with this one. We get 2x squared over 2, or just x squared, plus x, or sorry, minus x. This one we're evaluating from 1/2 to 2. All right, so now we're going to plug in our values. So 1/2 squared is 1/4 minus 1/2. So we'll have that negative out front, minus, and then we plug in 0, we just get 0. All right, we're adding to that. We're going to plug in the top number first. 2 squared is 4 minus 2 minus, and then we plug in the 1/2, 1/4 minus 1/2. All right, so now we want to combine all of this together. So I've got negative 1/4 plus 1/2 from right here, plus, and then 4 minus 2 is just 2, and then minus 1/4 plus 1/2. All right, so negative 1/4 and negative 1/4 would be negative 1/2, and 1/2 and 1/2 would be plus 1 plus 2. So I get 3 minus 1/2, which would give me 2.5, or 5 halves. All right, one more example. This one is a trig one. So we're going to have to remember those inverse trig rules, but here we go. We're integrating from, well, we don't need to separate this one. We can just go ahead and integrate. So the integral of 2 would just be 2x, and cosecant squared is cotangent. Well, negative cosecant squared is cotangent, so plus cotangent of x. And we're evaluating this one from pi fourths to pi halves. So we get 2 times pi halves plus cotangent of pi halves minus, and then we plug in pi fourths. 2 times pi fourths minus cotangent of pi fourths. All right. So 2 times pi halves is just pi, plus cotangent at pi halves is 0, minus 2 pi fourths is just pi halves, and then minus, well, it's minus a negative, so plus cotangent of pi fourths, which is 1. Did I do that right? Oh, that was supposed to be a plus right there. So this is going to be a minus 1. All right, so pi minus pi halves is pi halves, so we just have pi halves minus 1. All right, so let me go back and go over where I got this 0 and this 1, just in case you don't remember. Pi halves is up there at the top. So at the top of my circle, my unit circle, then I have the 0.01, r is 1. Now the cotangent ratio is x over y. So 0 over 1 gives me 0. And then for the cotangent of pi fourths, we've got 1 square root of 2. Cotangent is, again, x over y, so 1 over 1 is 1. So that's where those numbers came from there. And so this is my answer. All right, so now we know how to evaluate a definite integral in a way other than just geometry. And we had already learned that the area under the curve is what we're finding whenever we evaluate a definite integral. So this gives me a way to now do at least some functions by integration versus a Riemann sum, or the limit of a Riemann sum. So this is a good way for us to now be able to find area under the curve.